Welcome everyone to the next webinar in the PPMD webinar series on therapeutics. Today we have Summit PLC, Richard Pye, who is the Head of Corporate Development and Communications, and John Tinsley, who's the Senior Director of Research and Development, are going to be talking to us now about their drug SMT C1100, which upregulates utrophin. If you participate in these calls before, you know somewhat how they work. Everyone on the line is on mute, but you have the ability to write questions into the chat box as we go. We'll try to get to those questions. We also received a number of questions in advance. We have those. Everyone has looked at them, and we are going to try to answer those. But I'm going to turn things over to Richard in a minute. He's going to go through his presentation. And basically, we will do the majority of questions at the end of the presentation, unless there's something that really just needs to be addressed right at that moment. And I will be sort of fielding those questions as you write them in. And if we miss anything, we will capture all of the questions you write in the chat box, and we have all the ones you sent earlier, and we'll try and get those answered after the fact. So with no further ado, I'm going to turn things over now to Richard.
Thanks very much, Sharon. And firstly, I'd just like to start off by thanking PPMD for kindly hosting this webinar. It's the first time Summit has done one of these presentations, and we're certainly excited to be doing so because it really does provide us with a great opportunity for us to talk to the DMD community about our program, and in particular the positive progress that we have made during the last 12 months. Before we do start the formal part of the presentation, I just need to put up this forward-looking legal disclaimer, as we may have some forward-looking statements in the presentation itself. And also I'd just like to highlight that Summit is a publicly listed company here in the United Kingdom on the London Stock Exchange. And that means that we'll only be discussing today information that has already been made public, it's already in the public domain, and that any new information that we provide is always made through to the financial markets first in the form of press releases. Of course, people can keep up to date with news from the business by signing up for our email alert system or following us on Twitter, as we've recently ventured into the world of social media. And more information about both of these can be found on our company website. The address is www.summitplc.com. So 2012 has really been a year of great progress for us in terms of our utrophin program and our lead clinical candidate, SMT C1100. Due to the financial support that we've received from the DMD organisations, including parent projects, Summit was able to commence a phase 1 clinical trial on SMT C1100 in healthy volunteers, in which we evaluated the new formulation of the drug. Positive results from this trial were reported in October at the World Muscle Society Congress in Perth, and also later at the annual conference of Action Duchenne here in the United Kingdom that was held in November. And the results from this trial have been really encouraging, and John will review this in more detail during the presentation. Well, before we get into that, though, we would just like to talk a bit about the approach of utrophin modulation and highlight why we think it has the potential to be a treatment option for all the genetic variations of DMD. We'll also highlight briefly some of the data from non-clinical efficacy studies that has demonstrated the potential of SMT C1100. We'll also go through the phase 1 trial data, as I said, and John will then outline what the next steps will be for the program, after which we'll have a Q&A session. I'll now turn the call over to John Tinsley, who's my colleague. He's our Senior Director of Research and Development at Summit and has been involved in utrophin modulation as an approach for Duchenne's for many years, both with Summit but also in his earlier career, where he was a postdoctoral research fellow in the labs of Professor Kay Davis at Oxford University. And his work there generated a number of seminal Nature publications on utrophin and how its overexpression has the potential to become a treatment for all DMD patients. So with that, I'll turn it over to John.
Thanks very much, Richard. So, as Richard says, I'm going to briefly go through the rationale for why utrophin potentially can replace dystrophin, and also say a little bit about the normal biology of muscle where utrophin is naturally found, and how it interacts with dystrophin in the normal case, and how we believe that we can modulate utrophin such it can replace dystrophin in the Duchenne case. So dystrophin function in muscle. So importantly, muscle is made up of a large number. Each muscle is made up of a large number of individual fibers, and these fibers are very long. So if you imagine the length of a muscle going from your elbow to your wrist, then these individual fibers with a tiny diameter are well over a foot long. And so the way that muscle works is that it packs these little tiny fibers together in bundles, all of which are glued together with the extracellular matrix. And then these bundles then further glued together as groups of bundles to make up the whole muscle. So a good example of this kind of principle is in the kind of wires which are used in suspension bridges, which are made up of large numbers of small diameter wire fibers, but when they're fastened together, even if many of them get broken or damaged, they can still maintain the weight of the bridge, or in the case of muscle, still able to contract and relax. It's when you start to have many fibers which have damage along the length of them, so that as they contract and relax, the force can't be transmitted from one fiber to another, and that's when you start to get muscle weakness. And also because of the biology, you then start to get necrosis of muscles, and then with time you then start to fill in the muscle mass with fat and fibrosis. So it's very important the individual fibers are maintaining the integrity of these fibers. So dystrophin is the important component in these individual fibers, as this is the link between the inside of each individual fiber and the extracellular matrix, of the glue, and it acts as this molecular shock absorber. So as fibers contract and relax, they're not overstretched, and therefore damaging them. And also when the fibers relax again, they don't relax too much, and then start to the internal cytoskeleton then starts to sort of concertina on itself. And this loss of dystrophin, so the loss of the shock absorber, is what causes the damage to these fibers as they continue contracting and relaxing. And when the fibers become damaged, then they also start to lose their ability to contract and relax naturally because of leakage of things like calcium into the fibers. And that also then triggers up the natural degradative processes in these fibers, where the body is naturally trying to repair the damage. And this is done by degrading the damaged regions and then looking to replace with new bits of fiber. So in this situation, this is almost like having, if you've got damaged water pipes, you don't try and remove the whole pipe. What you do is you cut a section out and repair that, and that's essentially what the body is trying to do when there's individual regions of damage in an individual fiber. If we look at this level down as to how this repair takes place, and this here has a link between both dystrophin expression and localization in healthy muscle and utrophin expression in healthy muscle. So if we look on the left-hand side of this diagram, we see that there's a healthy fiber. You have dystrophin localized along the length of the membrane, linking the extracellular matrix and the internal cytoskeleton of the fiber. If damage takes place, so say through exercise, and you damage a small region within the length of this fiber, you have a natural degradative process which removes the bulk of the material that makes up the fiber to allow it the patch to be generated. And this patch is generated through satellite cells which are sitting along the length of the fiber, become activated to generate individual myoblasts. Now, it's important to point out that these myoblasts are all expressing utrophin. So in this damaged area, there's no dystrophin, utrophin is found in all these myoblasts. And after time, these myoblasts actually then start to fuse together. So instead of being individual cells, the membranes start to fuse together to start the regenerative process of mending this point within the fiber. And over time, when the fusion takes place, you now have essentially the fiber is now intact again with this area filled in, which is still utrophin positive, linked to areas which are still dystrophin positive. And then over time, what happens is that utrophin expression, so the amount of utrophin protein is turned off, and the dystrophin is turned on, so you then move back to this cycle here of a single healthy fiber. What occurs when you're dystrophin deficient is you go through the natural repair process where there's damage to the fiber. You go through this same natural development of early myotubes, all of which are utrophin positive. You get to this point where you've essentially repaired the fiber with immature fibers, but because there's no dystrophin now to replace this utrophin, which is gradually turned off, so that there's a point where there's no utrophin or dystrophin, and you go through this continual cycle of regeneration and degeneration. So, in summary of what I've just said, we have a normal muscle fiber. So this is ongoing from very early development. So you have the fetal formation of myotubes and fetal muscle. Here they only express utrophin. So in these fibers, it is utrophin which is linking the extracellular matrix in the fiber bundles to the internal cytoskeleton of the fiber. As these fibers mature, so become bigger and are able to generate more tension in contraction and relaxation, they also now are expressing dystrophin. So now you can find dystrophin and utrophin localized to these fibers. And as they mature and become the final fiber of mature muscle, the utrophin protein has been turned off and is now completely dependent on dystrophin to make this link between the extracellular matrix and the internal cytoskeleton of the fiber. In the DMD muscle fiber, as I've described, you go through the same fetal development process up to the immature stages. However, the point where there is now no dystrophin present to replace the utrophin which is being turned off, you go into the regenerative phase. And what we're proposing is that in the DMD scenario where you're dystrophin deficient, a utrophin drug is able to maintain utrophin expression even as the fibers mature, such that in mature fibers, although there's no dystrophin present, you have this protein utrophin which is able to perform the majority of the functions that dystrophin has, even in mature muscle, so is able to be the shock absorber that's required to protect these fibers from being damaged and degenerating. To take this on a next step as to how there's a switch between utrophin expression and dystrophin expression requires a further delve down into the biology of muscle here. And so this complex looking diagram is really trying to describe what is happening in the nucleus, which was demonstrated in the fibers, and how utrophin protein is generated to form this shock absorber link between the internal cytoskeleton of an individual fiber and the extracellular matrix. And this is all dependent on the genes in the DNA in the nucleus are controlled by regulatory elements. So this is essentially these regulatory elements are essentially like a tap. So if you need expression of a particular gene, these regulatory elements are activated such that the tap is turned on to generate you the RNA, which is then modified and processed to generate the RNA which can make the protein, and then this RNA is translated to make the utrophin protein. So depending on how much the tap is turned on, you can generate even more RNA and therefore even more protein, or the tap can be turned off such that you have no RNA and eventually you will lose the protein. So this is the control system in all genes, and we're interested in today is particularly around the regulation of utrophin expression to control the amount of utrophin protein that you can get to form this important junction between the myofiber and the extracellular matrix. So in normal muscle, when dystrophin is now switched on and is able to take this role at the membrane and protect the membrane from damage, the utrophin tap is essentially turned off. So there's processes here which turn the control of utrophin transcription off, and once there's no RNA, then eventually there becomes no protein. So this is a situation where you have a mature fiber which is expressing dystrophin, and naturally utrophin has been turned off in these fibers. In the DMD fiber, although the dystrophin gene is active, you have no dystrophin protein to build up the complex protecting the fiber at the membrane. But also because the utrophin gene has been turned off, you also have no utrophin present to be able to replace dystrophin. So this is the situation in a DMD fiber. So what we're proposing with the approach that we've been developing is a utrophin transcriptional upregulator or modulator, which is able to take control of the tap and maintain the transcription of utrophin, and therefore if transcription is taking place and RNA is present, then you'll get protein from that. So even when there's no dystrophin present, because the compound is able to keep this tap switched on and even turned on higher than normal to make even more RNA and therefore more protein, then this potentially has a disease-modifying approach for DMD, which, as you can see, would be relevant potentially for all DMD boys. So this is what it looks like in muscle. So this is looking at dystrophin and utrophin protein in normal human muscle development. So along the top line here, where you can see the white, this is where dystrophin is localized using an antibody specific for dystrophin. And on the bottom panel is using an antibody specific for utrophin, and again the white areas are where utrophin is localized. So in the early developing fetus, you can see that if you have a look in muscle, you can see there's fibers which are dystrophin positive and utrophin positive. And then as time increases, and here's around birth, you can see that the amount of dystrophin is increasing, and such here in the 9-month-old infant, you see dystrophin at all the fibers. However, utrophin is still present, albeit decreasing in amounts even until after birth, whereas then in the fibers it's then been switched off and has now been completely replaced by dystrophin. So utrophin is naturally found in all muscle. It's expressed in early developing muscle, but it's still found even in adult muscle, where it now has a role at specialized junctions within the muscle, and these are areas where either the nerve contacts the muscle at the neuromuscular junction, or where the muscle is attached to the tendon. So even in adult muscle, you still find utrophin expression, but it's now in very specialist areas rather than being expressed from myonuclei along the whole length of the individual fiber. So the utrophin upregulation program, I said, we believe this is a disease-modifying approach for DMD, and I mean by disease-modifying, it's because you're trying to address the single defect which causes the disease, so the loss of dystrophin. And so if utrophin is able to replace dystrophin and we can keep those levels maintained, then we should be able to reduce significantly the disease, because we're replacing the function of dystrophin and therefore protecting muscle from further damage and all the additional problems that become from the degeneration and regeneration, such as activation of inflammation and fibrosis. So we believe this disease-modifying strategy has the potential utility for all DMD patients, and this would include both those from families with history of DMD and also the spontaneous mutations which occur in families. And this is actually a very well-characterized approach. So the loss of dystrophin causes DMD, and that's been known for decades. But also, over the past 20 years or so, there's been a lot of work on utrophin and showing that, to all intents and purposes, it can act as a very good stand-in for dystrophin and protect dystrophin-deficient muscle from damage. So the program that we're talking about here today has built on a lot of work that's been done in the University of Oxford from Kay Davis's lab and Steve Davis's group, both of these who are co-founders in Summit, and it's this collaboration which has led with Summit's work to the development of SMT C1100, which has been in the phase 1 trial. So I briefly want to show the effects that dosing animals with SMT C1100, so these are dystrophin-deficient animals, the effect that it can have, the beneficial effect that it has on these animals. And I'll specifically try and talk around things which, rather than just sort of individual sort of physiological process, but are much more relevant to the disease and reducing the disease. So firstly, it's important to show that if you dose cells with SMT C1100, you can increase the levels of utrophin. So these are DMD patient myoblasts, which have been treated with SMT C1100. And so, as I showed you in one of the previous diagrams, that myoblasts naturally express utrophin. However, when you add the drug, you've now essentially turned the utrophin tap on even further in these myoblasts. So this is a normal level of utrophin that they're making, and now as you increase the amount of drug present, you increase the amount of utrophin that's being made. As I showed you previously, these myoblasts are able to then fuse to form these very young myotubes, which is strings of myoblasts which are fused together, so they have the same membrane, but they contain a large number of nuclei. And even in this scenario where they're making utrophin, as you increase the amount of drug that's present, these myotubes are now even able to make even more utrophin. So this proves that the principle that SMT C1100 has this ability to increase the amount of utrophin levels through increasing the amount of RNA that's present. So, as I say, to turn the utrophin regulation tap open even further. So with this data, we then looked at dosing the dystrophin-deficient animals with the drug, so they're dosed with the drug once a day. And what we were keen to do was to test these animals in a paradigm which is as DMD-like as possible. And the way that you can exacerbate the disease in these mice is to force the mice to exercise. So these mice are forced to exercise on treadmills during the week and for several weeks. And what you can see in these mice is that they get a much more severe muscular dystrophy than if the mice were just allowed to remain sedentary in the cage. So this information here is actually looking at the pathology in the muscles of these mice. So this is an example of a large skeletal muscle in the mouse, and this is the diaphragm in the mouse, which is, as you're aware, is a major muscle to allow breathing to take place. So what can be seen from this actual data, and it's summarized here, is that if you dose these animals once a day with SMT C1100, over time you increase the numbers of normal fibers. So these are the larger diameter, more mature fibers that I've described you see in healthy muscle. And the reason why these fibers are still there is because we've stopped the utrophin tap from being turned off. And because there's a lot more normal, healthy fibers, we also show that there's a decrease in the number of the regenerating fibers. And so the regenerating fibers are these ones, which I've shown you, is when there's damage to a region of a fiber, you start to activate the repair process. So the repair process has been reduced in these muscles. And very importantly, the amount of necrosis that you see in the muscle, so the areas where it's completely dead, is also reduced dramatically. and by reducing this area of necrosis, you will then decrease the amount of inflammation and fibrosis that is taking place. So daily dosing of SMT C1100 has a dramatic effect in improving the pathology in the muscle of these mice, these forced exercise mice. So what does that do to the whole animal? So we're reducing the pathology in the muscle. What's it doing generally to the function of the muscle? So there's two experiments I want to go through here because I think it's important when you're actually starting to look at whole muscle function. So the first one is looking at grip strength. So grip strength you can maintain because you're able to contract muscles and they remain contracted. If muscle is more and more damaged, then it reduces the ability to maintain a grip. So if you imagine you want to open a door, and so you hold the handle. If the door opens very easily, you don't have to have much grip strength to make that movement and open the door. If the door is difficult to open, you have to grip much harder and pull much harder to be able to open that door. And there comes a point, for instance, if the door's locked, that you will eventually try to grip the handle, but you will be unable to maintain that grip, and your hand will be pulled away from the handle. This experiment is essentially doing the same thing, but using the forced exercise mice. And the axis here is really a measure of the amount of grip that these animals can maintain until they've essentially pulled off the equivalent of the door handle. So these are just normal mice here in the blue box, and they maintain a certain grip strength before they're unable to hold for any longer. Here is the dystrophin deficient MDX mouse, but it's the sedentary animals. So these are what just essentially sit in the cage and are minding their own business. If you take these mice, but actually put them through the forced exercise procedure for a number of weeks, you can see that within 4 weeks or so, they are unable to maintain grip strength for very long. So they have a very weak grip strength. However, if you take these animals and you dose them daily with SMT C1100 for 4 weeks or so, you can see that these animals now are able to maintain grip strength to exactly the same level as wild-type mice. So what you saw in the previous slide showing the repair to the muscle pathology and the increased amount of healthier fibers now translates across to showing that these animals can maintain a very significant grip strength. If we look now to another endpoint, which again is looking at the whole muscle, is the ability of muscle to fatigue. So muscle fatigue is a much more complex process because not only moving muscles having to contract and relax in a very synchronous way, there's also a number of other factors such as oxygenation and other things, which means that muscles can fatigue. So this experiment is, we believe, is analogous to the 6-minute walk distance test, which is the primary efficacy endpoint in the patient trials. So in this panel here, if we look at the black dotted line, so this is essentially the forced exercise mice over a period of 5 weeks. And you can see the dramatic drop in these mice in the distance that they can continue running and walking on a treadmill. So within 4 weeks, the distance that they can walk on the treadmill falls from around 200 meters down to around 100 meters, and at 5 weeks it's down to about 75 meters. So there's a significant drop in the distance that they can walk in 5 weeks. If you take these same mice but you dose them with SMT C1100 daily, you see there is also this similar fall within the first 4 weeks or so. But if you remember, this is the time when muscle is really starting to regenerate and start to increase in its health. And there becomes a point where actually continued forced exercise, it becomes stabilized, and these mice now are able to continue walking at the same amount without this continued decrease. So essentially, after a period of time, dosing with SMT C1100 halts this increase in the fatigue that you see with forced exercise. And at the end point, we're seeing that after dosing them, we've increased the distance travelled in these mice by over 50%. Interestingly, if you do the same experiment but you give these mice steroid, prednisolone, you see a very profound beneficial effect, that even after 4 weeks that these mice are pretty much able to continue running on the treadmill as long as mice before they even started the forced exercise. So this is a very interesting observation, and this combination effect may be relevant moving into clinical trials, where one would imagine that most of the boys in these trials will still be on their normal steroid course. That covers the information around the biology of utrophin and how we think that maintaining utrophin expression for long term has significant benefit on muscle health and muscle strength. And so I'll now briefly go through the results that we found in the first clinical trial. And you must remember, this is the first clinical trial ever done on a compound to upregulate potential to upregulate utrophin. And as Richard already said at the beginning of this talk, we also have to thank the foundations which sponsored this trial, and if it wasn't for their internal thought process and allowed the money to be available to us to run this phase 1 trial, this data would not have been generated. So the phase 1 trial, so all phase 1 trials are really looking, the first thing is to see if you take a drug, that firstly it's safe over the time period that you take it. It's also important to know that you can actually take the drug. So if it's an oral drug, you can actually swallow it. It doesn't make you sick, doesn't make you feel poorly. And then you need to know that if you keep taking the drug, it still remains safe. So that's the primary objective, is to determine the safety, the tolerability, and move to taking multiple doses. So then the secondary objectives, when you're wanting to move on to the next clinical trials, and these will be clinical trials in patients, is how much drug do you need to take to have enough drug in the body to activate the mechanism that you want it to do. So in our case, we need to upregulate the amount of utrophin. So the secondary objective is to understand the relationship between the dose that you take and the amount that's in the blood. So the study it's a single dose first to check that it's safe and tolerated, and then you move to taking doses a number of times over a number of days, and to see what the level of the drug is in the blood, but also that it's still safe and you're tolerating it. So the part 1 is the single doses. So there were 4 groups that took the drug consecutively at these amounts, from 50 milligrams per kilogram moving up to 400 milligrams per kilo. So after each dose, the volunteers are then examined further over a period of time to make sure that there's no evidence of safety problems. Then you move on to the hundreds, etc., etc. And once you've seen what the single dose does, you can then, from this, make choices as to what you want the multiple dose to look like. And for us, we decided we wanted to look at groups where they actually took the dose twice a day, and they took two different doses, 100 milligrams per kg twice a day and 200 milligrams per kg twice a day. So importantly, in the trial, all the doses were safe and they were well tolerated. So in the time that they took the drug, there was no adverse events recorded, apart from an association with pale stools as the highest doses were taken, so the single 400 milligrams per kg or the 200 milligrams per kg twice a day. And this pale stool was caused because of actual compounds which wasn't absorbed and was actually passed through the body. Looking at the safety aspects, so looking at things like blood pressure and pulse rate and the heart, so all of this related to the heart, and then looking at clinical laboratory evaluation from serum and also the physical examination, all the volunteers with any dose that was tested with remained within the normal limits. So, as I say, the doses were safe and they were well tolerated. So moving on to looking at the amount of compound that's present in the body. So this is the PK, so this is the pharmacokinetics, so this is how does the dose that you take relate to the amount of drug that's found in the blood. One of the things we need to do is to generate or identify the amount of drug that we want to see present in the blood. And so the levels that we looked at are related to the amount of drug that you need both to add to cells to see significant increases in utrophin expression, but also the levels that we saw in the forced exercise MGX mouse to generate the data that I've just shown you. So we ended up with an amount. This is an amount of drugs around 0.2 micromolar, which you want to see in the blood to be able to significantly increase the amount of the activation of utrophin transcription and therefore the amount of utrophin protein. So this is a fairly arbitrary amount which is easily detectable, and that's the level that I'll talk about for the next few slides. And this data also came from the ongoing collaboration in Professor Kay Davis's group. So with that figure in mind, we then looked at the amount of drug in the plasma. So this is the single dose. So we're looking at, so this is the average from each of the healthy volunteer groups. This is the time, so blood is taken at these time points here, and this is the amount of drug that's in the plasma. So as we increased the dose, the amount of SMT C1100 went up in the plasma, and with the single doses on average, they all had above the activity level that we want for the whole time that we looked at it. So this gave us a lot of confidence that we can now move on to do the multiple dosing, and the next couple of slides shows that information. So this is looking at as I said, the multiple doses. So what I'm looking at, showing here, is just the 100 milligrams per kilo dose that was taken morning and night, and it was taken so essentially twice a day for 10 days. Now, this graph shows the area under the curve. So this is the sort of total amount of drug that's present within a 12-hour period. Here are the individual healthy volunteers which took the drug, so 100 milligrams per kg twice a day for 10 days. And what you could see in the majority of the individuals, the drug level fell by around 25 to 30%, and then it remained stable. And you can see with each individual, they had different levels of drug present. But the important point was on repeat dosing, although it only fell slightly to around 75% of what they started taking, and it remained stable for the remainder of the time. If we now actually look at the levels of these individuals in the last sort of 12-hour time period, so on here I've marked this sort of 0.2 micromolar level of drug that's required to increase utrophin activity 50% above the normal levels that they make. Again, you can see there's this variability between the individuals. However, in all cases, individuals were above this 0.2 micromolar level for several hours in every 12 hours. And some of these actually, they never fell below this level within the 12-hour period. But even in the lower ones, for several hours, they will have been able to make utrophin RNA for several hours, and this RNA will continue being processed to make more protein. So the trial conclusions, importantly, this formulation that we used, and it's important to say that the formulation is appropriate for the pediatric population. So it's a flavored suspension which is taken orally, using a cup. There's no significant adverse events. So the single doses I've showed increased the SMT C1100 plasma levels above that required to increase natural utrophin expression. And when we dosed repeatedly, so twice a day for 10 days, as I say, there was this initial fall in the plasma levels of SMT C1100, but this then stabilized after 4 days. And most importantly, all the volunteers were above this level required to increase utrophin expression for at least 60% of the time. So in the worst case scenario is that if the DMD patient took this twice a day, then the utrophin would be switched on for at least 14 hours of that day. And the RNA that's generated in that 14 hours will continue to be translated to make utrophin protein, which is able to localize to the membrane and protect these fibers. And importantly, the levels that we see in the volunteers are similar or greater than the levels that we see in the blood of the MDX mice, where I've just shown the significant benefit. So the data shown here strongly supports the progression of SMT C1100 into the next stages of clinical development. So the next steps. So it's important that we pause and think about the translational path for utrophin regulation. So as I've said, this is the first time anybody's ever moved a product like this into the clinic. And the next steps are very important because we want to do the right thing and we want to do it quickly and we want to learn the lessons that are now available from previous trials in DMD. And so at the moment we're talking to a lot of leading pediatric neurologists and DMD key opinion leaders. So to advance into the patient efficacy studies, so here when I talk about efficacy studies, I mean the agreed regulatory endpoint to show efficacy in the trials. So to do that, we initiated a biomarker program to quantify utrophin levels, to examine the effects on muscle regeneration and essentially muscle health, which in parallel to levels of utrophin. And so this is therefore looking at the earlier sort of the proof of concept to show that if you dose with SMT C1100, we can show we increase levels of utrophin and potentially show benefit to muscle health. To do the much longer studies, so these are things like 12 months dosing in a efficacy trial, we have to do some longer term safety studies, so toxicology studies, to allow the longer efficacy trials to take place. And we're developing the clinical plans which need to include this proof of mechanism, so prove that SMT C1100 administration increases the levels of utrophin. And if one can show that, then, as we've seen in the mouse, if you can maintain increased amounts of healthy muscle, then over time that will translate into increased muscle function and hopefully a positive outcome in an efficacy trial. So I think that covers where we are today. The outcome of the phase 1 trial is very exciting for us. It means that we can now plan to move into patient trials. And as I say, we're talking to a number of people about this because it's important that we do it right, and so that we don't mean that something that has potential becomes lost. So on that note, we shall finish and take questions.
Thank you, John. That was a really nice discussion, I think, of both the biology and the drug and where you are now. And I appreciate the fact that you put up that slide showing the support from so many different organizations. I think people often ask, why don't organizations work together? And I think that's a beautiful example. That wasn't done independently. We actually got permission from Summit to share information and data in our review process. And so all of those groups you saw as funders we discussed this, amongst ourselves and really shared information. So there is an example of the community pulling together, and it's an example of a drug that wouldn't be going forward without that nonprofit support. So when you wonder, what can I do? This is what you've done. You have put this drug back into development. So I think you'll appreciate John spent a long time describing the increase, the maintenance of the drug at the appropriate concentration in the blood. And that was an important step. That was just a key step because in the original formulation of the drug, it couldn't achieve those plasma levels. So that's what you saw the support, was to reformulate this drug and test it and show that you really could get the proper dosing. And you just heard from John, next steps now moving into clinical trials. It's very exciting. So we've received a number of questions during the presentation. I've been making notes. We'll try to get to as many of those as we can. I think, John, just to start, just to make sure everybody's on the same page, we've gotten a couple of questions about different mutations in dystrophin, questions about mutations in the dystrophin promoter. Maybe you meant the utrophin promoter. I wasn't sure. But could you clarify for people for whom utrophin upregulation could potentially be beneficial?
So we believe that it's beneficial because the similarity between the utrophin protein and the dystrophin protein is such that you can imagine that the utrophin is almost a fetal form of dystrophin, and therefore if you can maintain this fetal form throughout muscle maturation, then to all intents and purposes it should do the job of dystrophin. So regardless of the reasons why there's no dystrophin present, then utrophin upregulation should be able to, we believe, will be beneficial in all the boys.
Right. So that's the key, is that it wouldn't matter, if your son has a deletion, where the deletion was, or what type of mutation or point mutation in dystrophin, because what we're really doing is going around dystrophin and upregulating a different protein. So it's mutation-independent approach.
That's right, yes.
Yeah, so another question that came in, there was a couple of people asked this, so I think it's worth going over. There was a recent publication out from Dongxing Duan and a colleague Lai from the University of Missouri that talked about another molecule called nNOS and how the binding region of nNOS isn't present on utrophin, but it is present on dystrophin. And I think this confused a number of people because they're wondering now if this approach makes sense. If you can't have this nNOS protein, which we know is important, it does do things, but it clearly doesn't bind to utrophin. Does that mean that utrophin won't work as a stand-in for dystrophin?
That's an interesting observation, and I think where we see it is that the fundamental problem to first attack is to build the shock absorber back to muscle, and with that in place, you can then see what other issues there still might be, and one of these might be loss of nNOS. What we do know is that in the forced exercise MDX mouse, where we saw significant benefit, the assumption there is that they too there will be no nNOS localized at the membrane. Yet even in fatigue studies, it looks like we saw benefit, and certainly with the presence of steroids, we saw significant benefit. So that these mice still did not seem to fatigue. We saw significant benefit on reducing the muscle pathology and a large number of other endpoints. And I think this disease is made up of a number of pieces, and it's really identifying which is the biggest piece to have some benefit, and then can you add through other drugs, or maybe you don't need them for certain. Some of these things aren't required for certain muscle functions, for instance. Is that nNOS required all the time, or is it only required if you really want to do a lot of exercise? So I think we accept that utrophin does have some differences to dystrophin, but I think the important point is to start getting utrophin or dystrophin back to the membrane and see what effect that has. And then these other things may just be subtle effects which may only sort of show incremental change to the disease, Whereas I think getting dystrophin or utrophin to the membrane will have quite a fundamental effect on the disease.
Right, and I think that paper was a little confusing because we've actually known for a very long time that utrophin doesn't have the ability to bind to nNOS. That paper was just a minor refinement on that idea. And the other thing that I think is important is that, this seems like a little bit of an esoteric question for all of you out there going, what is nNOS? It's an enzyme, and it may be involved with maintaining blood flow to the muscle during exercise. But we also know that there are approved drugs, Cialis and tadalafil, for example, that are on the market now for erectile dysfunction. But they can actually increase the amount of nNOS that's active, and to the point where you do get restored blood flow, even if you can't bind nNOS to dystrophin, because we know this works in boys with Duchenne. You can still activate that molecule, so it doesn't have to be bound to dystrophin or utrophin at the surface of the cell. So there are ways to get around that. So let's put that question to bed for now, and say that, it looks like, at least from the evidence in the animal studies, that just getting utrophin upregulated is enough, that nNOS might be a different problem that can be dealt with separately.
And related to what you say there, Sharon, when we made the overexpressing utrophin transgenic mice, then again, presumably there's no nNOS present there, but those mice, to all intents and purposes, were cured.
Right.
Including...
Well, there is nNOS, it's just not localized to the surface of the cell. So I think you could probably still activate it in other ways. So moving on to some other questions people asked that I thought were very interesting and important. Someone is interested in cardiac function. Have you looked at cardiac function, and do you have any idea if the protein can affect that?
We've not looked specifically at cardiac function. What we do know from the mouse studies was that we could see increased levels of utrophin protein in the hearts of these forced exercise mice. There is evidence in the literature to show that if you overexpress utrophin in the MDX mouse, you can have benefit on the cardiac function in the MDX mouse. So we believe that potentially that utrophin localization in cardiomyocytes may also be beneficial.
Okay, thanks. So I think other questions people have asked, and I think something that I'm interested in, is what is the potential for combining an approach like upregulating utrophin with other drugs that are out there, either other utrophin upregulators or even completely different approaches?
I think that there's a real possibility that combinations could be beneficial, and I think that the first point is that muscle presumably has a number of points along the membrane where you attach dystrophin and the complex, and so the first thing to do is to make sure that all of those sites are fully occupied, and you could do that with dystrophin. However, if the levels of dystrophin are low, you may be able to then continue occupying those sites with utrophin. So I think a utrophin localization and dystrophin localization in muscle potentially would be beneficial. So all the dystrophin modulating approaches, and then so lots of the other problems are around inflammation and fibrosis, and that's all because you have this very active degeneration and regeneration going on. So if you slow that down, you may reduce the signals to recruit inflammatory cells and fibroblasts, but also then being able to dampen that down further with anti-inflammatories or antifibrotics, again, I could imagine would be beneficial. So I think as time goes on, depending what the data is from the primary trials, then sort of the polypharmacy could be very an approach that one would take.
Okay, I think there's also obviously a lot of interest in the planned therapeutic trials, and I know you may not be able to answer all of these questions because you can't really talk about anything new or specific plans without doing that in particular forums because of being a public company. But if you could comment a little bit on what countries you think the first trials might take place in. We've had questions about when there would be trials in the U.S., would there be trials in Serbia, would there be trials in Brazil? So to the extent that you're able, if you could just maybe expand a little bit on the plans for drug development.
Certainly, yeah, that's a good question, Sharon. We get that a lot in terms of location of future trials and the details around them. I think at this stage we're still planning what the next patient trials will look like, or the first patient trials for C1100 will look like, and I think until we've got those plans in place, it's very hard for us to be precise in terms of what they will look like. I do think, though, that we can look at what previous studies have been done and what shape they have taken. If you look at the work, say, that PTC and Procenza have done, it does look like we'll need to do at least 2 trials in patients, and John will talk about those in a moment. But I think they conducted trials in many sites, both within Europe and the US, and I think we could envisage something similar happening with us at this stage. We should also add that although the phase 1 trial was conducted within the UK, that's not going to have any impact on the location of future patient studies, and that was a healthy volunteer trial. So again, I think what's important for us is that we ensure that the design of the patient trial is correct, that we're providing C1100 and utrophin upregulation with the best possible chance of being successful and being improved both within the US, Europe and other countries around the world as quickly as we possibly can. So I think that's probably the best answer we could give at this stage.
Okay, but is it safe to think that you'll probably be looking for approval in multiple countries, ultimately?
Yeah, I think that's right. I think the ideal scenario is that you file in the US and Europe and potentially other areas at the same time, and for the community, that's what one would want to do. But I think also our thoughts around how we're planning trials, that would be the sensible commercial thing to do. And right. I think that, so, where individual trials take place is one thing, but the commercial plan would be that you want to get it filed in all the areas simultaneously as possible.
So there are also questions coming in because I think people really want to understand the scope of what's needed next, and sort of what is, and this is something you probably can't answer until you understand exactly what the next trials are. But do you have a plan for funding this next phase of the study? Do you have an idea what the expense will be, and to the extent that you're able, if you?
We'll try and answer those as best we can. I think in terms of the plan for the next trial, we would be looking to go into patients, so it wouldn't be another healthy volunteer trial. We've done that piece of the work. It is now to move on into DMD boys. And the first part of that process will be to look at the tolerability of the drug. We need to identify the doses that we want to use in longer term trials in the patients as well, and then move into the actual longer term activity study. I think there's a number of processes by which we can achieve this different scenario, and the times and the costs associated with that will be determined by what the final plan is, and that's something we are discussing closely with DMD clinicians, both again within the UK but also within the US as well, and we're identifying the right experts that we want to work with to ensure that we have got that correct trial design. I think, again, we can't stress enough that it is vital we get that study correct, and we give particularly SMT C1100 the best chance of being successful, and that will allow us then to sort of open up its use to more patients if that does work. In terms of how fast and what rate of progress we can make with it, I mean, to date we've been relatively limited on that, and I think sort of historically that was down to the fact that the program took an unexpected turn, shall we say, in 2010 when our former development partner handed the rights back to us. And it meant we had this valuable asset back on our books, which we've been unable to progress. It wasn't part of our budgets at the time. But thanks to sort of the work we had done and the support of the community, we've been able to get it back into a phase 1 trial. But it means that our resources still remain relatively constrained, and what we've had to do has been quite linear, the work. Studies are being done sequentially, and that's why the first piece of work we did was to do this phase 1 trial, show that the new formulation works, that we're getting good exposure of certainly higher concentrations of the drug in the blood plasma. But it means that there is the other work that John outlined, to do with, say, the biomarkers, the longer-term toxicology work, and it's because we needed to get the answer to the formulation before we could really move on to doing those other studies. And I think if we had greater flexibility financially, we could maybe look to do some of this in parallel, doing it a bit more at risk. But we've got to sort of be cognizant that we are a company with other activities, although D&D is a central part of our work. But we've got to make sure we do things that's appropriate for us. But I think we're very committed to the area, and I think that's been highlighted by the work that we have done.
Yeah, I think the mere fact that you've taken this drug back and really pushed to develop it, I know you've pushed because I've experienced that, demonstrates there's a strong internal commitment. I think people are really interested in the details of what the next study would look like, what the eligibility requirements, that sort of thing are going to be. And I think what I hear you saying is that these things haven't really been determined yet, that you're doing your diligence now to make sure that you've learned from the other trials that have gone on and that you're in the process of designing those now. Is that correct?
Yes, I would say that's the situation we're certainly in now, and whether it's going to be sort of specific mutations or age groups, things like that, they're all factors which we need to look at. One thing we probably could say is patients being on steroids, we don't see that being an issue. That was one of the reasons why we did the in vivo work in the MDX model, where we co-dosed with prednisolone, because we knew most of the boys are likely to be on steroids, and therefore we wanted to check there wasn't any issues. Actually, we were pleased to see the exact opposite, where there was a really strong benefit when co-dosing. But I think all these are things which we need to get into our plans first, and then we'll be in a much better position to comment on them.
So just a final question then, because we're right on the hour. Will you come back and update us again when you have those details worked out? And certainly we'd love to hear from you at the Connect conference this summer.
I mean, certainly when we have the plans in place and we're moving forward, then we'll be happy to update people. I think you can see that, to my mind, the trial process is 3 things that you need to do, and you can either run that as 3 individual trials, or you start to use some of the clever sort of adaptive trials that people are starting to use now. So the first thing you need to know is, what dose do I want to give somebody for a long time? So this is a long time, is a year plus. So you need to know that piece of information. We need to be confident that when you dose with SMT C1100, we start to see increases in utrophin and maybe changes in muscle. So that's sort of like an activity trial, a proof of concept. And then the third trial is the efficacy trial, so the regulatory trial where you're looking to get approval. So there's 3 pieces of activity. All of them are as important as each other. You could do that as a very linear process. So you do some PK and dosing in the boys, then you wait a while, and then you do an activity trial, and you wait a while, and then you do the efficacy trial. Or can we actually start to put some more of these things together where actually, dependent on data, you can then start to adapt the trial to bring more patients in and move it to efficacy. So that's the bit that we're really trying to work. If you do everything all in one go, it obviously costs a huge amount of money, because essentially you're doing one trial, which gets you all the way through to the regulatory approval. Or you do things in a linear approach where you wait and see the data, and if it looks good, you can move on. If it doesn't look so good, then you have to think about it. That obviously takes more time, but there's less cash at risk. So we're really trying to find the middle ground, which means we can do the best job as we can for SMT C1100 and for the community. And those are the decisions that we're making at the moment.
All right. Well, I want to thank you, Richard and John, so much for joining us and sharing this information. If you have asked a question that didn't get answered on this call, we're going to go back through the transcript, and we have the questions. So we'll cross-reference those, and we will try to get answers for those later. And this presentation, I think, will be available afterwards. Is that what we have decided?
It'll be available by next week.
By next week, we will have that available
on the website.
Yeah, on the PPMD website. So Thank you very much. We appreciate you joining us, and we will sign off now.
Thanks very much, Sharon, and for hosting this. It was very kind, and we appreciated the opportunity. Thank you.
Okay, thank you all. Have a nice day. Bye-bye.